So this is my lecture 11. So in the last class, we were discussing digital control systems, and we saw that sample and hold operation plays an important role in digital control system, and also for analyzing a digital control system, analyzing of signals in digital control system, we used jet transformation. In case of continuous time systems, what do we use? We use Laplace transformation. Now we'll discuss the jet transformation of systems. In the last class, we saw the jet transformation of signals. Now we'll consider if a if a signal, if a sampled signal goes to a continuous time plant, then how will you analyze the system behavior, or in fact the transfer function of the input output, if sampling is there in a system input. So jet transformation of jet transform of systems. Jet transform of systems. Suppose this is my system configuration. So ut is my input, and then it is sampled. This is T sampler. This is T sampler. That means this switch is closed at every T interval. And this is your, then as per our notation, sampled signal we denote as U star T, and GT is the impulse response of the system, suppose. So GT is impulse response. So what is the objective? Objective is, what is the objective here? Objective to find a relation, between CZ and UZ. So from this figure you can see that the input is sampled but the output is not sampled. So then the question may arise, how will you obtain CZ? Because jet transformation is applied for continuous for sampled signal. So there is no sampling as such involved. So therefore, to obtain this relation, we will use some fictitious sampling. So this is your suppose T sampler again, but now it is fictitious sampler. It's fictitious sampling. This is a fictitious sampling. Just I am writing fictitious sampling. because if you do not consider this, then how will you get CZ? So that's why I have considered it. So this is a fictitious thing. This actually really it is not present. But for analyzing, we have to obtain transfer function between CZ and UZ. That's why I have considered this one. So now, what is your CT? Now, CT equal to what? Using convolution theorem, T is equal to 0 to infinity. You can write U star tau into G of T minus tau dt. Convolution is because input signal is U star, or you can also write U star T into G of U star T minus tau into G tau d tau. That also you can write this same thing. So this means CT equal to zero to infinity. So now what is your U star tau sampled signal expression we have already got. This is equal to summation of n equal to 0 to infinity any sampling instant into unt into delta of time domain expression into e to the power minus ts or something was there. So if you take a time domain expression, then it will be delta of tau minus nt. So this is your u star t. We have already got this relation in the last class. And then g of t minus tau d tau. So this implies CT you can write like this. Now this expression, when you will evaluate, this expression will hold only when delta function is not equal to 0. So when delta function is not equal to 0 at tau equal to nt. So then what is the value of this integration? This integration value will be, this is a well-known result, n equal to 0 to infinity u of nt into, just you will replace this tau by nt. So this is g of t minus nt. Okay. So now what is the Z transformation of CT? On the other hand, so Z transformation of CT is what? So Z transformation of CT you can write, although here it is continuous time signal. So Z transformation of this one, Z of CT you can write only when the CT is sampled. This is definition. This is equal to CZ. This is equal to CZ. This is equal to what? Summation of n equal to 0 to infinity into C of nt into Z to the power of minus n. So this is the definition of Z transformation. So now C of now we'll substitute what is CNT. So CT is known. CT we have determined. CT is this one. So then what is your CNT? So CZ you can write CZ equal to summation of n equal to 0 to infinity. So this derivation is important, because unless until you derive the relation between CZ and UZ, ultimately we want to show that the CZ equal to GZ into UZ. In case of continuous time system, also we saw we show in our control engineering class that CS equal to GS in TVS. Professor Saurabh Patra, I am sure, has shown that one. So now for discrete time, we have to solve CZ equal to GZ into UZ using convolution results, discrete time convolution. So CZ equal to n equal to 0 to infinity, n equal to 0 to infinity, then this is your, what is your CNT? CNT you can write like this, summation of, so here also n equal to 0, so n is any dummy variable. I will write m equal to 0 to infinity, u of mt. Now in place of t, what will you write? T, I will write m, n, g of, and n I will replace by m. So n minus m. So this upper bar means it is bracket into t. Bracket I have not written. I could have written bracket, but this means n minus 1 first bracket into t. Okay. So already one bracket is there, so that's why to avoid that, to avoid another bracket, I have used upper bar. So this into z to the power of minus n. So from here, go to next page. From here, what you can write? CZ equal to. So now if you take the summation, this summation out, summation of m equal to 0 to infinity, if I can take out umt into summation of, because there is no n involved, n equal to 0 to infinity, g of n minus m into t into z to the power of minus n. Okay, so this implies Cz equal to summation of m equal to 0 to infinity umt into summation of, now n minus m, suppose k. So n minus m, so put n minus m equal to k. So n minus m, if you put k, then what happens? N equal to 0 means what? K equal to minus m. So k equal to minus m to infinity g of kt into, now n will replace by m plus k, so it will be minus k into z to the power minus m. Okay, this will imply your cz equal to summation of m equal to 0 to infinity u of mt into summation of k equal to into z to the power minus m, z to the power minus m into summation of into z to the power of minus m, the summation of k equal to, because ultimately GT is an impulse, GT is the impulse response of a causal system. So k equal to minus m to 0, k equal to minus m to 0, the output is 0, gkt equal to 0. So so I need not to consider the instant from k equal to minus m to just before 0. That means negative instant I need not to consider. So k equal to 0 to infinity g of kt into z to the power minus k. So now What is your CZ? CZ will be equal to, what is this value? This value is your UZ. And what is your this value? This value is your, this is your GZ as per the definition. So this implies ultimately, so this implies CZ will be equal to GZ into UZ. So this is an important relation. Yes, CISO system I have considered, so it does not matter whether UZ into GZ or GZ into UZ. So you can also also extend it to MIMO system. At the time when I have considered this one, you have to be careful a little bit. So UMT for example, UMT I should write, I should write here. If it is a MIMO system, multi-input, multi-output, then I should write G of n minus m into t into UMT, because UMT G n minus m into t is operating on UMT. So I have written UMT before. So if you do that, then you will get GZ into UZ. But anyway, this is a CISO system I have considered. The derivation is correct. That is not the problem. But only in case of MIMO system, only you have to be careful here. That means, as I said, that CZ G optimize to UNT. So what is the observation? Observation is this one. Observation is Z transformation of system. Z transform of a system is the Z transform of its impulse response. Okay. Another thing is that, so convolution in time domain. So here, so discrete time domain. Convolution we have taken here, no? So convolution in discrete time domain. Convolution in discrete time domain is equivalent to algebraic product in Z domain. So convolution in time domain was equivalent to algebraic product in S domain. Now convolution in discrete time domain, convolution in continuous time domain is equivalent to algebraic product in S domain. Now convolution in discrete time domain is equivalent to algebraic product in Z domain. Okay, so these are the conclusion important. Now you can easily extend this result. For example, if you take this kind of configuration, if there are multiple G1, G2, suppose this is your G1 T, and then suppose this is your G2T, this is your CT, this is your UT, this is your U start T. So suppose T samplers, this is T sampler, this is T sampler. Okay, so then this is equivalent to, as we have seen in case of a single block. So now here also this is equivalent to So this is suppose your C1t, C1t, this is your C1 start t. So, well, before writing this one, from using the above result, what you can get? Using the above result, Cz equal to what? G2z into C1z, and again C1z equal to G1z G1z into uz. So this implies, so then this implies what? Cz equal to G2z into G1z into uz. Or you can also write in this way: uz, then G1z, then your C1z, G2z, and then CZ. So that means this sampled block, sampler along with this continuous time block, I have converted into an equivalent discrete time system. Equivalent. So this is an equivalent and discrete time system for this sampled system. So you can it is difficult to analyze this system sample data. So if you convert it into discrete time, equivalent discrete time model, then you can easily analyze, as we will see now, stability study and all these things, response, what will the response, all these things you can study. Now, so what is in case of 1 by, so how will you realize one G1 GS GZ? In case of continuous time system, we have seen that GS you can realize it in canonical form. Different canonical forms are there, but at the time, what is the dynamic? What is the unit we have used? 1 by S. But here, 1 by S was at the time. In case of continuous time system, 1 by S was an integrator. 1 by S is an integrator. But similarly, GZ also you can, given a GZ transfer function, so you can also realize using block diagram. Then at that time 1 by S has to be replaced by 1 by Z. But 1 by Z implies what actually? So 1 by, what is the physical meaning of 1 by Z? 1 by Z, the significance of 1 by Z. Because 1 by Z is an important unit in discrete time system or sample data system. So significance of 1 by Z is very important. The significance of this transfer function. 1 by Z means actually what? That means, because 1 by Z, every time we will use when we will implement a general transfer function GZ. Implement using, say, block diagram. Realization of GZ using block diagram at the time 1 by Z. So what is the meaning of 1 by Z unit? So suppose this is your UZ and this is your YZ. Now YZ equal to 1 by Z into UZ. So if you give a signal here, then what will the property of the discrete time signal? Then That means what if you give some UKT, then what will be the your YKT? That we want to see. That means then we'll be able to see what is the meaning of 1 by z. Y by yz is what? Yz is z inverse. Sorry, it's not capital Z, small z. Yz is z inverse from there, for z inverse into uz. So this is equal to what? Z inverse. What is uz? Summation of n equal to 0 to infinity unt into z to the power minus n. So this is definition of z transformation of uz, ukt, that means uz. This implies what is yz? Yz is equal to summation of n equal to 0 to infinity u of nt into z to the power of minus of n plus 1. Okay. So this can be written like this. Yz is what? Summation of n equal to 0 to infinity. So now suppose n plus 1 equal to m. So put n plus n equal to 0 means what? M equal to n tends to n equal to 0 means what? M equal to 1. So m equal to 1 to m equal to 1 to infinity u of. So now n equal to what? N equal to m minus 1. So u of m minus 1 into z to the power minus m. On the other hand, what is yz? Yz you can also write like this: summation of m equal to 0 to infinity ym. So m minus 1 into t, actually t term is there, ymt into z to the power minus m. So here minus m. So that means what you are seeing, so comparing these two equations, what you see, if you give some ymt, then what will be umt, then what will be your ymt? Ymt will be just the delayed version of umt. That means ymt from here, ymt equal to u of m minus 1 into t. So ymt equal to u of m minus 1 into t. So this implies y of mt equal to u of, so m equal to 0 is not valid here because because we are assuming it is a causal signal. U, y all are causal signal. So before t equal to 0 instant, they do not exist. That means if we apply y0, so m equal to 1, 2 after dot dot. So if you apply y0, then what will be your y is yeah, if you apply y0 means y0 means here y1. So y1 equal to u0, y1 equal to u0, y2 equal to u1, and so on. So this implies what? 1 by z is a unit delay operator. This is very important result. Unit delay operator. That means whatever input you will apply at an instant, output will appear here after 1 unit delay. Okay, after 1 unit delay. So at an instant, if you apply say ut, then that effect you will get after 1 unit 1 sample time. Okay, 1 sample time t. So in general, this result you can generalize. So in general, Z transformation of u of k minus n and t is there, so I am not writing that t every time. K minus n equal to z to the power of minus n into z transform of uk. Okay, t better to write. So this is t. So this is equal to z to the power minus n into uz. Okay. Similarly, this is z transformation of, this is also an important result, u of k plus n into t. So here also I have used defined again. Why I have put bracket? Inner bracket was not needed. K minus n t. Okay, so z transformation of k minus n t. So here it will be z to the power n. So if you take just apply the z transformation formula, you will directly get this. You please try check it. Minus summation of k equal to 0 to infinity uk into z to the power minus k. It's now minus k. Okay. And so next two important results will show, that is initial value theorem and final value theorem. So initial value theorem. So in case of Laplace transform also we have seen. So if you have a signal yt, then initial value of yt is limit y of 0 equal to limit y is a causal signal. So that is before t equal to 0, it does not exist. Then y of 0 will be equal to limit s tends to 0, limit it was limit s tends to infinity. It was limit s tends to infinity into sys. Now and the final value was y infinity equal to limit s tends to 0 sys. So now we'll see. Now we'll see the initial value theorem is from Z transformation. So y0, if you have signal, sampled signal ykt, then y0 equal to limit z tends to infinity into, now in case of continuous time signal, y0 equal to limit s tends to infinity ys. and final value is y infinity will limit s tends to 1, s tends to 0, s into ys. So here y0 is limit z tends to infinity, z tends to infinity, yz. And you can easily prove this because why? So you can easily see what is your yz equal to, you can easily see yz is your summation of y of nt into z to the power minus n, k equal to, sorry, n equal to 0 to infinity. So this is this, you can write also like y0 plus yt into z to the power of z to the power minus this is t, I will not write unnecessary. Okay, t also you can write, it is not the problem. T you can write. T you can write. So this is y0 plus yt into z to the power of minus 1 plus after dot y infinity into, okay, plus after dot. Then this will imply what? Now from this you can easily see, if you take limit z tends to infinity, then except y0 the other terms will vanish. So ultimately then y0 will be this one. Similarly, final value theorem. Final value theorem, y infinity equal to limit. So this result is important. So final value theorem, or limit z tends to 1, y infinity, y0 means, actually here y infinity means limit, I should write y infinity means k tends to infinity yk. So this is equal to z tends to 1 z minus 1 into yz. Okay, so z minus 1 into yz. So this means, of course, here yk is bounded. Otherwise, final value will not exist. Final value will be infinity. So you can prove it also. Just small proof, outline of proof I am just showing here as I have shown. So you just take z transformation of yk plus 1 minus yk. So if you take z transformation of y of k plus 1 minus yk, so this will be ultimately equal to summation of k equal to 0 to infinity into y of k plus 1 into z to the power minus k minus summation of k equal to 0 to infinity yk into z to the power minus k. So this will give you, this is equal to what? This is equal to ultimately, well, now, so this is the expression for like now. Now, if you take what is z transformation of yk plus 1 minus yk, you can also write from the above results, these two results, this result, it will be z into zyz, it will be z into yz minus z into y naught, zyz minus, you can easily see, zyz minus n equal to here 1, yk plus 1, n equal to 1. So zyz minus z into y naught. y naught. Okay. Minus yz. So this will be equal to z minus 1 into yz minus zy naught. This implies limit z tends to 1 z transformation of yk plus 1 minus yk. This will be equal to just, you can write limit z tends to 1 z minus 1 into yz minus y0. Now on the other hand, from this expression, you just put z tends to 1, then what will you get? On the other hand, from 1, say, suppose this is 1, limit z tends to 1, z of yk plus 1 minus yk is equal to what? Equal to just, it will be y infinity minus y0. You just check it. Just if you expand it, only y infinity will only the infinity due to this term will be present. Other term will get cancelled, and y0 will present from this term, because here k equal to 0 means y1. So from 2 and 3, then from 2 and 3 we get what? Limit z tends to 1, z minus 1 into yz. This is equal to y infinity. So this is good. Okay, this is not, it is a little bit difficult, but not that much. But initial value proof is very simple. That's why I have written in the bracket. Now, well, so what is the stability in case of if you obtain a system? Suppose if you are given a system like this or the system like this, then how to analyze the stability? In case of a continuous time system, we saw the the transfer function, that means gz and gs, the poles of the transfer functions are lying the left half of S plane, then it is a stable system. Now, what do you mean by the stability of discrete time system, or you can say yes, discrete time transfer function. So stability of gz. So stability of discrete time system. dt system is discrete time. So how do you analyze stability of discrete time system? Suppose I consider gz equal to z by z minus a. Okay. So now what is the output? Then this implies what is output? Impulse response, or it is called pulse response. Pulse response yk. Yk will be what? Z inverse of just z, inverse z transformation. Inverse z transformation, if you do, what will the value? So z transformation. So this is the z transformation of some standard transfer function, standard signal a to the power k. So inverse z transformation will be what? Yk will be a to the power of k. Okay. So this implies what? For stability of Gz, What should be the condition? Mod A should be less than 1, because otherwise what will happen? As k increases, it will increase. So if mod A is less than 1, then yt will be bounded. Yt will as k increases, yt will reduce and come down to 0. So that means in that case gz will be stable. So gz is stable if mod A is less than 1. So similarly, suppose gz is this one, 1 by say z minus A into z minus B. So this transfer function you can write like this. This transfer function you can express like this transfer function can be written like this: inverse transform impulse response of this system, a to the power k plus a q2 into b to the power k, like that. So q1 q2 are constant. So here also you can see that yk is stable if mod A is less than 0, as less than 1, as well as mod B is less than 1. So that means, what is the implication? So 1 is playing an important role. So here then, for stability of this gz, mod A should be less than 1, as well as mod B should be less than 1. So we can at least say that for stability, this implies for stability of a given gz, for stability of a given gz, all its poles should lie within unit circle. This is very important result. So in case of continuous time system, left half of S plane is your stable region, and in case of discrete time system, unit circle, interior of unit circle is the stable region. So that means, suppose this is real of z, this is your imaginary of z, then you can draw a circle. So this is your unit circle. Zero. This is your unit circle. So this is a unit circle, and poles should lie within this unit circle. Okay. And so just I'm writing poles, the interior of unit circle with origin, unit circle with center at origin. Interior of unit circle is stable region, and the outside unit circle is unstable region. Outside unit circle is 8 unit circle as shown is unstable region. This is stable, this is unstable. Okay, so this is a stable region. Okay, so now okay, stable region is bound. In case of discrete time system, the the j omega axis on the left half of S plane, in case of discrete time, in case of continuous time system, left half of S plane is stable and right half of S plane is unstable. So in case of discrete time system, how mapping you can do? That means left half of S plane is transformed into is left half of S plane is uh, mapped into interior of unit circle. Okay, unit circle in Z plane, and the right half of S plane is mapped into exterior of unit circle in Z plane. Okay, and what about j omega axis? J omega axis is mapped into the circumference of the unit circle. So this one means j omega axis in your S plane. So that just the point I'm writing. So these are important point. So first point is the left half of S plane is mapped into the unit circle of Z plane as shown here. This one, unit circle means unit circle with center at origin. So, and the right half of S plane is mapped into the exterior of the unit circle in Z plane, and j omega axis in S plane is mapped into the boundary of stability, boundary between stability and instability. So j omega axis in S plane is mapped into the circumference of the unit circle in Z plane. Okay, these are the important results. Now you should for a good design here, for a good system, how will you say that, okay, if the system is stable, if the pole locations, if the poles lies inside unit circle, but then the question may arise, then pole lie means which side of the unit circle, left side or right side? So which side is good as far as stability is concerned? So that I will just discuss through a very simple example. There are some mathematical derivation, but that I am not going into that. That is done in digital control class. So just one example. Just I'll no the question I'll just form. So which side of the unit circle means question is which um, for a good system, for a well-behaved system, for a well-behaved stable system, for a well-behaved stable system, For a well-behaved stable system, the poles of well system Gz, the poles of Gz should lie in the left half lobe, in the right half of the inside the should lie in the right half of interior, in the right half of right half of the interior part, right half of the interior part of unit circle in jet plane. So why? So I am saying that this is the for a good design. I am saying that for good design, I am saying okay. I am saying that for a good design. So this is the. So I am saying for a good, for a well-behaved system. So for a well-behaved system, the pole location should lie here. For a well-behaved system, well-behaved stable system. So this is the region where the pole location should lie. Why? For well-behaved stable system, pole location should lie here. This is stable the whole interior, but the right side of the unit circle is the is a region where the well-behaved system should lie. Now, just to explain this just I will illustrate through an example. So here, for example, I will take two systems. One is G1Z equal to Z by Z minus 0.5. Okay, and G2Z I will take as Z by Z plus 0.5. So both are that A-wise both are same, just the numerator polynomial is same and denominator polynomial. What is happening? In one case, one root will lie in the right side, that means here. Another case, root is lying here. Both are stable system. So both are stable, but whose behavior is good? So you can see here. Then what is here? Y1k. Y1k you can easily find. This is 0.5 to the power k. And what is your Y2k? Is minus 0.5 to the power k. So if you take the response, so what will the response of Y1 and what will the response of Y2? So this is your Y1k and this is your Y2k. So how it will look like? Y1k will be, suppose k equal to 0. K equal to 0 means it is 1, and then k equal to 1. K equal to 1 means 0.5. Suppose k equal to 0, this is, and then suppose 1 means 0.5. Then k equal to 2. So k equal to 2 means a 0.25. 0.25 k equal to 2, and then k equal to 3 means 0.125 and so on. So the response will be like this. But here if you see, so k equal to 0, k equal to 0 means 1, k equal to 0 means 1, but k equal to 1 means, now you see, k equal to 1, k equal to 0, 1, k equal to 1 means here minus 0.5 here. So directly it will come like this. Then k equal to 2 means again positive, 0.25. So it will be like this. So the response will be like this. Okay, so you can see this response is not ringing or oscillatory, but here you see that this response will oscillate. So it is not a good behavior. So this response is a well behaved system, well behaved, well behaved. So it is not well behaved because oscillatory. So for a well-behaved system, so this implies for a well-behaved system, so your mm, this implies for a well-behaved system, for a well-behaved stable system, the poles should lie in the right half of lie in the right half of unit circle. Right half of unit circle as shown in the figure. So as shown means here I have shown right half of unit circle. Okay, fine. So now the one 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 interesting thing I will discuss, that is your, as I said, that given a given a feedback system. Now we consider feedback system. So the sample data feedback system is there. How do you analyze stability? And in the last class, we towards the beginning of the digital control part, so I said that the sampling time plays an important role, and if you increase the sampling time, then what will happen? Increase the sampling time means the stability reduces, stability of the feedback system reduces, and if you decrease the sampling time, stability of the system increases. So, but that I want to see, and how to analyze stability of a feedback system. So that means for that purpose, what you have to do, we have to obtain equivalent feedback system. Given a sample data feedback system, you have to obtain an equivalent discrete time feedback system. Then you can study stability. So we'll see. So now stability study. At least stability is very important for any system, any feedback system. So stability of sample data system, stability analysis, stability analysis, stability analysis of sample data feedback system, of sample data feedback system. Feedback. So stability analysis we have seen for a stable GZ, the pole should lie within unit circle. Now for sample data system, the sample data feedback system, how do you analyze stability? So suppose this is your sample data system. So as I said, in case of sample data system, plant is continuous time. Then this is the feedback diagram of a standard sample data system, zeroth order hold. Then your digital controller, CZ, and then your sampler. This is your feedback system. This is your Y. Here YT, and this is your RT. negative. So this is your T sampler, and this is also on fictitious sampling should be there. Otherwise, you will not be for analysis purpose. This is not present in practice, but this is fictitious sampler that you have to assume. So here your ET tracking error. This is your E star T. So this is your hold output UHT, and this is your suppose okay. So this is your hold output. So now what I have to do? So here some intermediate. So here also it will be sampled signal because your this is your digital processor, digital controller, and this is your continuous time planned, This is a zeroth order hold, GH. This is a GH. So here also the signal is sampled signal. So sampled signal is coming because because you're after digital controller. So analog to digital, digital to analog signal. Then analog signal will be converted. It will be hold. So here the signal is actually sampled signal. So the here we can write something like that. U start T say here signal is actually sampled signal. You need not to include again. You can include it another sampler, but we need not to include here another sampling. We need not to show. So here, what is your transfer function between y star t, ys and us? So yz and uz. So transfer function. So transfer function. So here what is my plant? This is my controller. So this I can write like this. This is your RZ. This is your EZ, and then your CZ, and then this is your GPZ. This is your YZ. So this diagram can be written like this because what is a GPZ? GPZ is transfer function between YZ and UZ. GPZ is transfer function between YZ and UZ, and CZ is what? CZ is transfer function between again UZ and EZ. And what is your EZ? EZ is RZ minus RZ minus your YZ. So when RZ you are considering also here you should use input sampler. Many I have not considered and I have not shown that. But this is your fictitious, this kind of fictitious sampler. You should also consider there fictitious sampler. Okay, at the input, so as to have RZ. So anyway, that you can show. That means there is no harm. So you can represent like this, where GPZ is what? GPZ is Z transform of what? GS into Z transform of Laplace inverse of GS into GHS. So this is very important relation. Z transformation of Laplace inverse. So I should write it clearly. Z transformation of Laplace inverse of GS into GHS. Because GS and GHS, it is in Laplace transform. So you have to take Laplace inverse to obtain this continuous time representation. Then that signal, then you have to take Z transformation. Then only you will get the relation between YZ and UZ. So this implies GPZ equal to Z transformation of Laplace inverse of. So what is G8Z? G8Z we know. What is G8Z? 1 minus e to the power minus Ts by S. This is your whole transfer function into GS. Now, what is your e to the power St? Actually, Z, what is the relation between S and Z? Z equal to e to the power of St. So this equivalent transfer function of the plant. So now you can write like this: GPZ. GPZ is what? Z transform of. Okay. So if you put e to the power St equal to Z, so it will be just 1 minus Z inverse. You can bring inside, outside. So this will be Z transform of Laplace inverse of GS by S, where e to the power minus St equal to Z. Where, not where, since e to the power S minus St equal to Z. So this implies ultimately GPZ equal to 1 minus Z inverse into Z transform of Laplace inverse of GS by S. So this is very important relation. So given a feedback system, what will be the equivalent plant? Controller is digital, suppose CZ. You have so now what is your equivalent plant? Equivalent plant GPZ will be this one. A very important relation to study stability, or to not only stability. Now you can analyze the behavior of the system. All the things will remain same. Only now the analysis you have to do in discrete time domain, and the stability unit will be, stability region will be unit circle. So for example, one simple system we'll take, one exercise we will consider. One exercise we will consider. So exercise is GS equal to, suppose, 1 over S plus 1, and CZ equal to some simple gain K, and T equal to, say, 1 second. So here GS is equal to 1 over S plus 1, and CZ equal to just simple gain, proportional controller, and T is sampling time is 1 second. So determine the range of gain K. So determine the range of gain K for closed loop stability. Closed loop stability, and comment on your result as compared to its continuous time. Comment on your result based on the range, based on the range, based on the range, based on the range in continuous time. based on the range in continuous time system. If you use a continuous time system, a continuous time feedback system, then what range of gain you will get, and what range of gain you are getting, then ultimately you compare. Okay, so the solution. So here, what is your GPZ? GPZ is 1 minus Z inverse into Z transformation of Laplace inverse of GS by S. So GS is 1 over S plus 1 and then S. So this implies GPZ is what? 1 minus Z inverse into Z transformation of what is Laplace inverse of this one. So to get Laplace inverse, you can do partial factorization. So what is S equal to 0 if you put, then it will be 1, and S equal to minus 1 if you put, it will be minus 1. So then will imply this will imply GPZ equal to 1 minus Z inverse into Z transformation. So this will be Z transformation of Z transformation of what? This will be unit 1t1 minus, this will be e to the power of minus t. Okay, so this will imply GPZ will be 1 minus Z inverse into what will be one unit step function. It will be Z by Z minus 1, and what is e to the power minus t? Z by, so t is what? T equal to kt. So k e to the power minus t. So now capital T is e to the power Z minus e to the power minus t. Minus t is minus t. So this implies GPZ will be equal to, ultimately, if you simplify it and put t equal to 1, so it will be 1 minus, it will, please simplify it. I am not simplifying. I am not showing the details. So put t equal to 1 second. So in GPZ you will get like this. So now what is the closed loop characteristic equation? Then the closed loop characteristics. Closed loop characteristic equation becomes 1 plus k into, from this figure, 1 plus c into GZ, 1 plus c into, this is a negative feedback system. Yeah, negative feedback system. 1 plus c into 1 plus GPZ into CZ equal to 0. This means 1 plus GPZ is what? 1 minus e to the power minus 1 divided by Z minus e to the power minus 1 into CZ is 1. What? K equal to 0. So this will imply. So now we have to find what is the range of gain K for closed loop stability. So you can easily, that the one easy way is to do using root locus. Now what is your loop transfer function? So this is equal to 1 plus LZ equal to 0. So this where L is K into LZ. So it will divided by Z minus e to the minus 1. So now if you draw the root locus, how it will look like? The root locus will look like this. This is real of root locus, same thing. Just now the stability region will be the different. So here first you should draw the unit circle. Same thing like continuous time domain, only the unit size, all the rules of root locus will be valid. So here, what is the open loop pole location? Open loop pole is z equal e to the power minus 1. So e to the power minus 1, e to the power, so e to the power minus 1 value, e to the power minus 1 value you have to first. So z equal to e to the power minus 1. So e lies between 2 and 3. So e to the power minus 1 will be like somewhere here. So it is e to the power minus 1. So and no zero local zero. So as you increase, so how the roots will go. So roots will go like this. So here k equal to 0 and here k equal to infinity. Okay. So and here what is your z? So here z equal to minus 1. So that means you have to find what is the value of k. So here k equal to 0. So this will be the value of k max for stability. What is k max? K max should satisfy from root locus. K max should satisfy what? K max should be, so from root locus minus 1 should be equal to, that means minus 1 1 plus k into Lz equal to 0. So 1 plus k into Lz equal to 0, what? That is minus 1 equal to minus k into Lz should be equal to minus 1. That means your k into Lz. So k max into Lz is what? 1 minus e to the power 1 by max. What is the value of z? Z equal to minus 1. So minus 1 into 1 plus e to the power minus 1 should be equal to minus 1, because k into Lz should be equal to minus 1. So this is one Lz at z equal to 1. This is your Lz at z equal to 1. So k max should be equal to then 1 plus e to the power minus 1 divided by 1 minus e to the power minus 1. So this is, you will be calculate, it will be 2.16. This will imply for closed loop stability stability 0 less than k less than 2.16. So this is very important result for this system. So this is the range for closed loop stability. Now if you use, suppose if you do not use any sampling and if you use a continuous time feedback system with proportional controller k and this, and then naturally you will get your loop transfer function will be k by s plus 1. In case of discrete time system, it will be for k by s plus 1 loop transfer function. Then what will the gain merge? What will be your range of k and k? K is 0 to infinity. Okay. So that means for continuous time system, for continuous time feedback system, feedback here for stability zero less than k less than infinity. So now you see here upper range, because of sampling, upper range sampling time t equal to 1. So it has drastically reduced. The stability region has drastically reduced. So this implies what? Stability region region reduced drastically because of sampling. So this is the problem with sample data system. So in case of continuous time system, you will get continuous time feedback system, you will get infinite. But if you use sample data system, that is digital control, if you implement the controller digitally, then that you have to stability will reduce. Okay. So just one exercise I am giving here. So I will also include one assignment. So those who are interested, you should solve the assignment problems also. So one exercise just I am giving here. One exercise. So suppose GS is equal to now 1 by S into S plus 1 and CZ equal to K and T equal to 0.1 second. Determine the range of determine the range of gain K for closed loop stability. Loop stability. So answer is K is less than 21. Please check it. You can solve it. This one similar same method. Okay. So just 1 second, I will see if I have missed something. So fictitious sampling is important because to take jet transformation. So here no sampling is involved in CT. CT we are not sampling, but if you want to find relation between UZ and CZ, you have to obtain a fictitious sampling. You have to consider. This is not actually present, but you have to consider for analyzing the system. So initial value theorem, final value theorem is also important. Similarly, in case of the proportional error constant, steady state error, all the relation will hold. Just the final value theorem, final value result and initial value result will change. Kp proportional error constant, velocity error constant, and then acceleration error constant, all the things will also arise just with slight change because of this final theorem is definition is different. Final value theorem result is different. So stability is very important. This is the stability. This is the main difference between the discrete time system and continuous time system. So stability becomes only the interior of unit circle. And also for a good design, your closed loop pole should lie in the right half of this stable location, right half of this unit circle, in the right half of the interior of unit circle. Otherwise, you will get that ringing behavior as we have explained in this example. And ultimately, here conclusion we have drawn is that the sample data system or digitization means that if you implement a continuous time system using a digital processor, then what you have to sacrifice, your stability boundary will reduce. So for example, here for this particular problem, if you do not use any sampling operation, and if you use continuous time feedback system, your loop transfer function is K by S plus 1. So if you draw the root locus directly, you will get infinite gain margin here. But here you can see because of this boundary. So now the gain, the stability region is constant because of this boundary. So this is your unit circle. So this is the stability boundary. the part of the root locus you should lie within this unit circle for stability. That means all the roots of the roots should lie within unit circle. So, okay. Okay, this much is for today. Thank you. Next class we'll start the how to design controller in digital gen. What kind of difference will arise in digital control system compared to the analog controller design. Thank you.